Real-time operating systems have been around for decades, and so you might think that there isn't a lot of innovation really happening within the kernel itself. Well, as it turns out, that isn't actually the case. Today, we are going to be talking about a new innovation in real-time operating system kernels known as cycle-based scheduling. Now, have you ever worked with a real-time operating system only to discover that it didn't have the resolution to schedule or delay tasks below a millisecond? You probably had to write a bunch of your own application code outside the context of the RTOS. Well, this is, fine, I guess. It should have made you suspicious whether the application was actually meeting its deadlines, was maintainable, and actually scalable. Now, shouldn't your RTOS be able to manage the timing of the entire application, not just the timing that happens at a millisecond or longer? So that timing should be well below a millisecond as well, right? So as you probably know, balancing temporal precision and energy efficiency can actually be a constant struggle for developers and managers in the embedded systems domain. The demand for precise timing control grows as the application evolves, right? It's not just set in stone. And so whether you're working in automotive, IoT, medical devices, or even industrial automation, you're going to find that timing is extraordinarily important. And the limitation of being limited to the system tick's 1 millisecond system tick is actually quite handcuffing to a lot of architects and developers, okay? Now, while, it is effective in managing real-time tasks, traditional RTOS solutions often fall short in two critical areas for us. First of all, what you're going to find is that the system tick itself is inefficient, okay? The periodic system tick, while it helps us keep kind of this precise system clock and timing, it actually causes the CPU to run and use energy when there are no tasks scheduled, okay? So you're basically constantly waking up your CPU even though you don't need to. Now, what does this do? Well, of course, it wastes energy, it wastes CPU computing power, and it can actually, to some degree, even increase the complexity of your applications, okay? Now, this is particularly important if you're working in low energy or battery operated devices, but just because you're connected to a grid doesn't mean that it's not also still important, okay? Now, there are RTOSes that have tried to overcome this limitation by introducing tickless power savings modes. And while these solutions are interesting and useful, what you'll find is that they almost seem like a band-aid. They seem like they're hinting at an underlying innovation in real-time operating systems that they just aren't quite achieving, okay? And as it turns out, this is really where this cycle-based scheduling comes into play, okay? So what we're going to do in this session today is we are going to talk about cycle-based scheduling in real-time operating systems. And I'm going to show you how we can actually very precisely schedule tasks, whether they occur in a microsecond or less, or a millisecond or longer. Okay, so this is going to be how an RTOS can leverage cycle-based timing. All right, so we're going to cover a couple of things here in this little short video. I just told you what the problem is, right? Energy efficiency, we're wasting cycles. We don't have precise control over the timing of our software. I'm going to actually show you a little demonstration of how the cycle-based scheduling works. So I'm going to share with you my setup so that if you want, you can actually duplicate this yourself. I'll show you the difference between system tick-based and this cycle-based scheduling. And then I actually have a demo that I've put together that will show you the differences between these two. And then at the end, I'll show you how you can actually try this in your own applications. All right, so with that in mind, the setup that I'm using today, in case you do want to duplicate it, is pretty simple. I'm going with actually all tools from SEGGER, okay? So you can go to one place to get them. I'm actually using SEGGER's Embedded Studio version 8.18, just in case, newer versions come out by the time you see this video. So this is going to be my IDE, all right, that I'm going to be using. I've actually got a real-time operating system from SEGGER that I'm going to be using. I'm going to be using embOS-Basic to demonstrate this to you. And I'm also going to be using embOS-Ultra, okay, which is a cycle-based real-time operating system, okay, and we'll be able to see what those differences are. Now, I've got the same application that I'm going to run using both of those real-time operating systems. And I'm going to be using SEGGER system view to record the events that are actually occurring in the application when it runs. Okay. And so that's going to allow me to visualize a little bit what the actual real-time operating systems are doing. And it's going to help us see what the difference between using a standard periodic system tick is compared to the cycle-based scheduling. And then I'm doing all of this on the SEGGER mPower board. All right. And, I'm nothing simulated, no smoke and mirrors or anything like that that's going on with this. You can actually see here right there. I've got the development board up and running, and it is connected to my computer. And I've actually got one of the demo applications running on there right now. But there's nothing very interesting that that you can visually see with the demo board. I'm just kind of showing you there that yes, this code is actually running on hardware. Okay, it's not a simulation. Okay, so as I mentioned, we're going to be looking at embOS-Base and embOS-Ultra. One of these is kind of your traditional periodic tick-based RTOSes, which is embOS-Base, and then embOS-Ultra is the one that supports the cycle-based scheduling, which is kind of, I think, the new innovation and kind of a very cool way of looking at things. Now, when we think about our traditional real-time operating systems, what we're typically doing here is we're using the system tick to perform everything, to basically kick off our kernel and say, hey, is there something that needs to be done or not? Yes or no, right? Well, what ends up happening with these systems is that we often have this system tick just kind of running periodically. And as you can see here on the slide, the system tick is running here. Maybe this timing is, maybe it's a millisecond, maybe it's 10 milliseconds. For our discussion, it really doesn't matter. But what's happening here is you got this periodic system tick going on in the background. It's one of the highest priorities in the task in the system. And what you're finding is that on most system ticks, there's not really much for the system to do, right? And so you're potentially waking your system up and the system tick is running. It's running a whole bunch of code and saying, yeah, there's nothing to do. Let's go back to sleep, right? That's fairly inefficient. If you're on a battery-powered device, that's not going to be good, right? And so what ends up happening here is that we have these things running constantly in the background, and maybe occasionally we have an interrupt service routine that runs, and occasionally the kernel is actually going to run in the background as well. Maybe when something needs to execute here, you can see I've got a high priority task here. System tick runs. It actually says, hey, we need to run the kernel, schedule a task, run the task. Maybe a secondary task needs to run. The kernel would probably actually run again, and then we'd have some delay while we wait for the next system tick to occur. Okay, and so the problem with this is, again, system tick's always running in the background. It's wasting resources. It's potentially wasting energy. Not really the situation that we want, but it's something that we've been living with forever, right? If you're working in low power devices, how do we solve the problem of system ticks being wasted? Well, we use these tickless modes where we try to put the system to sleep for a long time and we extend out the timing of our system tick. And while, yes, that works, like I said before, that's actually kind of a band-aid solution, right? It really hints at what I think the true solution is, which is to use cycle-based scheduling. Now, in cycle-based scheduling, what happens here is that the kernel isn't just using a periodic tick. What's actually happening is there is a one-shot timer that runs in the background, okay? And, the kernel basically says, oh, there's no tasks that are scheduled for, let's say, 2 milliseconds. And so instead of having a periodic system tick run twice, the one-shot timer is actually set to expire at 2 milliseconds. And so what happens is the system can go to sleep, it stays asleep, and when that one-shot timer expires, that's when the system tick occurs. It then, might run the kernel, and then run the other two tasks, and then it puts the system back to sleep, and then we have no ticks until, again, the one-shot timer expires based on when the next task is supposed to execute. Maybe it's 2 milliseconds from now, or maybe the next task that has to run is, turns out being 500 microseconds, right? And so in that case, the system will sleep for 500 microseconds, the next system tick will occur, and then that particular task will run, and then again the kernel will schedule whatever the one-shot timer needs to be set at. Okay. Now what this does is it removes the unnecessary need to wake the system up, the unnecessary need for system ticks when you don't need them. But secondly, it improves the resolution of our real-time operating system. Most RTOSes out there, if you go and use a lot of the open source ones, and even a lot of commercial ones, you're going to find that they don't allow you to schedule anything less than a millisecond. And as I mentioned earlier, that's going to add additional latency. It's going to remove precision from your code, or it might even force you to start doing things outside the real-time operating system in order to get that higher resolution timing that you need. And when you pull things out of the RTOS, you're really fracturing your software architecture. You're making it more difficult to figure out what's actually, what's your system doing. You start to kind of, like I said, band-aid things together, which really means at the end of the day, it's going to be more costly to maintain your code. You're going to have a lot of extra technical debt. You're going to have, perhaps bugs that occur because you're trying to do things outside the RTOS. And it just ends up being a situation that could be, I think, dramatically improved. Okay. Now, as you think about that, you're saying, oh, wow, using a one-shot timer. Okay, that's pretty interesting, right? But what about my system timing, right? I don't know about you, but I rely a lot of times on that periodic system tick to give me, how long has my system actually been up? A lot of times in applications I work on, whether it's medical or space systems or whatever it is, we have some type of telemetry that says, hey, at the 2-second mark, here's the telemetry. And at the 10-second mark, here's the telemetry. And here's the telemetry from 100 milliseconds and 200 milliseconds and so on and so forth, right? Well, when that happens, how do I maintain my time if I just have a one-shot timer? Well, as it turns out, what embOS-Ultra actually does is it allows you to set up a secondary timer that just kind of free runs that allows you to still keep track of that system tick. So you don't actually lose out on having that system tick with you, okay? So what you end up with is still the ability to have, hey, this is my system uptime, while also taking advantage of maximum low power modes, and also, like I said, improving the latency and the precision of your real-time operating system. Okay, so that's kind of the idea here of this cycle-based timing, all right? It basically allows you to dynamically schedule when that system tick needs to occur, instead of relying on a periodic system tick, okay? Now, as I mentioned, the whole idea of a tickless mode, that allows you to extend out and basically skip system ticks, but it doesn't give you that capability to increase the resolution and the precision of your scheduling within your RTOS-based application. Okay, so now that we kind of have an idea of how this looks, let's actually dive in and let's take a look at some examples. Okay, let me actually demo to you the differences here. So what I have here is, as I mentioned, I actually went out to the SEGGER website. I downloaded the demos for embOS Base and embOS-Ultra. All right. I made some minor modifications so that they'll run, on the development board. Some of the examples actually ran on the simulator that comes with the Embedded Studio, SEGGER Embedded Studio. But what I did in any event is it's a real simple application that you can see right here. All it has is 2 tasks. One task wants to run every 50 milliseconds. The other wants to run every 201 milliseconds. Okay. From there, you can see here we just, based on embOS Base and embOS-Ultra, based on the user guides, this is kind of how we go through and start to set up the stacks, the test control blocks and all that kind of stuff. And then you can see here, we have a high priority task and a low priority task. All these tasks are doing for this example is they're just blinking some LEDs and performing a delay. Okay. Now the high priority task is also sending out once every second. It's saying this is how many times the system tick interrupt has actually occurred. So every time the system tick interrupt runs, we're basically counting. Hey, 1, 2, 3. Okay. And it's just keeping track how many system ticks occur in a single second. And we're just going to report that out to the terminal. Okay. So those are going to be the only 2 tasks that are running on this. You can see here we have a simple little main function here that initializes embOS, our hardware, our board support package for our LEDs, and then we basically create our tasks and we start the kernel for the RTOS. Okay, and then it's going to go and it's going to run in the background. All right. Now, there's a couple different ways that we're going to look at the differences between your typical periodic tick that's scheduled versus your cycle-based scheduling that we do. So what I'm going to do here is I'm going to start with the traditional periodic tick. Okay. So I'm going to actually I'm going to build this really quick. So you can see here, nice and quick. Now I'm going to run it. So I'm going to actually put this on my target board. And that will just take it a moment if I click on it correctly. There we go. Okay. So you can see here, we're actually in our main application. And from here, I am going to click run. Now it's running in, a couple of seconds have been going by. You can see here that there's some reporting going on by that high priority task. It's actually reporting that there is a system tick interrupts per second, and it's very consistent. It's at 1,000. Now, I know looking at that video, you're like, man, that's very tiny text. So what I'm going to do here is I'm actually going to say export this to a text file, and you should be able to see now here that it's reporting out, hey, we're getting 1,000 ticks per second. And so our RTOS system tick is set to a millisecond, And this is traditionally what you would expect to see if you're using an RTOS, okay? Now, I can visualize this, right? So I've got this text-based one that I'm looking at here. That's great. Let's actually use system view, though. So I've got SEGGER system view fired up here. I can, one of the things you want to make sure that you do is come into recorder configuration. Make sure the configuration set up. I'm using a J-Link. So that's set. I have it set for RTT control block detection is auto using USB. And the part that is used on this M power board is actually an MK66FN. Okay, so that's already been configured here for me. If you're trying this yourself to try to experiment with this, you select whatever your target happens to be. Okay, so for this anyways, I'm going to click OK. I'm just going to click run. And what's happening here, as you can see here in this top part, it's recording events that are occurring that are occurring within the RTOS, okay? And a lot of these events are things like, hey, I'm entering an ISR, I'm exiting an ISR, I'm executing a function and things like that, okay? But the thing we want to see that's, I think, the most interesting is you can see right here, I'm going to stop this because it'll keep recording data here. You can see that there is a timeline here, okay? I'm going to drag that out, and you can see here that this is recording those events, and I can actually zoom in here. And as I zoom in, what you'll start to see here is that these are my periodic ticks. Okay, these are my system ticks. If we actually look here on the left-hand side, you can see this is the system tick, the scheduler, the HP task, the LP task, and then the idle time. Or are they just idle, right? Because we have an idle task in the background. If I'm not doing anything, I'm idle, right? And idle is where we would go into a low-power mode. Now, as you can see here, that the periodic tick is very consistent. You can see here the spacing between each of these ticks is 976.6 microseconds, okay? Now, you might be saying, Jacob, why is it 976.6 microseconds and not 1,000? Well, the reason for that is if I were to actually take this and I scroll in a little bit here, I'm going to scroll over and we'll zoom in here so that you can see a little bit more of the timeline. What you'll actually see here is that I have my system tick occurs, and the system tick is executing for 23.3 microseconds. So there's code in there that has to execute. Then after that, you can see the kernel runs for a little bit, 11.6 microseconds, and then followed by 16.1 microseconds of my high priority task actually executing. Okay, you can see here even that there's a little bit of a delay from when the high priority task is ready to execute, and when it is, it's 5.1 microseconds. And then you can see the kernel actually does run again right after my task before the system would be allowed to go into an idle state or in a low power state. Okay, and so if you actually add all those up, you end up with like 23.3 microseconds of code execution time, and so that's why we don't have exactly 1,000 microseconds between tasks. Right? It's from the end of the code execution to the beginning of the next system tick. Essentially, is what we're getting there. Okay, and you can also see some cool features here with system view. You can see here that we can see what our CPU load graph is. So you can see here while our tasks are running, we're obviously at 100% CPU because we're executing code, right? But if you zoomed out far enough, you could get a general feel for what the CPU load of your application on average is. And then on top of that, you can see here that there are some statistics that are kept track of. And you can actually see right here that our idle task for this application is running 97.47% of the time, okay? Which is great, right? We like it when we have some extra headroom to be able to expand our application. But kind of with that background, as I mentioned, if I zoom back out here, you can see that we have this periodic task that's executing. And I actually misspoke a little bit earlier there. You can see this is 942.7 microseconds in between when all that extra task ran and when the next tick begins. Okay, so typically if it's just a tick running, it's 976.6. If I actually have a task running, then it's going to be 942.7. But that's kind of beside the point here for this particular video. You can see we have these periodic ticks, and right here you can see we had a task we had to run, but right here, none of these other ones, we're just kind of wasting CPU cycles, not being very efficient. Okay, so what about our cycle-based scheduling? All right, well, I'm glad that you guys asked. So from there, what we'll do here is I'm going to stop my debug session, and I'm going to load up my cycle-based application that uses embOS-Ultra. All right, so if I load that application up, let's see, I made a little modification there. All right, so what we're going to see here is, here's my application. It's essentially the exact same thing that I had before, okay? The only difference is, as I mentioned, I'm now referencing the embOS-Ultra real-time operating system instead of the embOS base, okay? That's the only difference. You can see here again, I got a high priority task. It's reporting in milliseconds, every millisecond, how many system ticks there were, okay? Low priority task is toggling LEDs again. This is exactly the same type of code that we had before. Okay, so just the only thing that's changed is some of the library code I'm accessing. It's now a little bit different than it was. Okay, but other than that, it's essentially the exact same application. So what I want to do here is I'm going to build this guy again, and then I'm going to debug him on target. So I'm going to go ahead there, click go, and then I am going to let it run. Okay, so my code is actually running in the background. If you're curious, you can see, again, blinky LEDs are running on my development board, so we're in good shape there. You can also see, again, that every second I'm getting ticks out to my terminal, okay? So if I right-click on this again, export to text editor, this is what I get now. I'm getting typically 24 or 25 system ticks per second, okay? This is very different than the periodic system tick, where I was getting 1,000 every single time. Now you might be saying, well, wait a second, Jacob. Okay, this is, using cycle-based timing. We're using, we have a system tick like once every 40th compared to the, 1 out of every 40 periodic ticks, we're getting a, cycle-based one. But my cycle-based ticks here, they're not consistent, right? I'm getting 24, and then I'm getting 25, and then I'm occasionally getting 24s. Like, why are we getting variation here, right? Well, the reason we're getting variation is that if you look back at our application, we do not have tasks that are running exactly at, on specific milliseconds, right? I've got one at 50 and one at 201. And what that does is it offsets the tasks a little bit, and it allows us to see when the cycle-based tick actually occurs, right? Because it's using that one-shot timer, it doesn't have to do it the exact same number of ticks every single second. It all completely depends on how those tasks line up and when they need to execute, okay? And so again, this is giving us improved latency and improved performance and even higher resolution control over when we need these tasks to actually execute. All right, which is, again, it's very exciting. Okay, so we can see here that there's a difference there already just based on the number of system ticks that are being reported. How does that actually make our application look? Well, what we can do here is we can jump over to our system view, and we can actually go ahead and pull our some data. We can record data on the development board and see what it's doing. Now, for embOS-Ultra, what I want to do, I actually got to set up the recorder here a little bit differently. So the J-Link is still what I want to use, but right now the system view doesn't automatically pull the location of the real-time library from SEGGER. So I actually have to manually put that address in. Now, for my compilation, the address actually ended up being here at this 5C8 address. And you might be saying, oh, Jacob, where'd you get this from? It's actually super easy to find this. Okay, so what I actually do, I'm going to go ahead and stop that. You can actually look at your output files. And if you go to your map file, all you're doing is you're searching for _SEGGER RTT. Okay, very common library that we use a lot for, to get debug information off of our targets. Okay, it's great for event recording and things like that, among many other things that the library does. Okay, but you can actually do a search for that in your map file, and you're going to see here, this is the address that it's located at. Okay, it's part of the SEGGER _RTT object there. All right, so once I have that, I would put that into the RTT control block detection area, specify the address, and then go ahead and click OK. All right, now what I want to do is I want to go and grab another trace. You can see here, I'm recording new events. The code is executing, which is fantastic. I'm going to go ahead and click stop here. And then let's see the difference. Okay, with a periodic system tick, it was always, if I combined everything, it was always at about that 1,000 microseconds, right? We saw it was like 947 microseconds. We saw the spacing. Well, look at the difference here on this trace. Okay, if I just kind of move out here, you can see that there's variation. This is about 49.9 over here. This one's 41.9. This one's 8.9 milliseconds. You can see here, especially as I start to scroll out, yes, there's a periodic or repeating pattern to the rate at which the tasks are executing, but I do not have that consistent periodic tick that I typically would see running in the background. Okay. And so, you can see here that the system tick varies a little bit. And this is where that cycle-based scheduling really comes into play here. Okay. Because there wasn't something to execute every millisecond, the one-shot timer said, no, I don't have to wait that long. And so it set whatever the delay time was and let the system do low power states or whatever it needed to do in an idle state in order to, basically get back performance for you and energy. And if we actually dive in here and look, I'm going to zoom in on some of this just so that you can kind of see the difference here. You can see there's no system ticks anywhere near here. These are 50 millisecond spacings here, right? You can see here there's quite a bit of space here in between these, and 10, 20, 30, 30, 40 milliseconds. There's nothing going on in here. Okay, there's just low power mode state essentially. Okay, but you can see here I zoom in here. Now if we zoom in here, the interesting thing is you can actually see the system tick doesn't run as long. We got the kernel running here. We've got our task running, and then again, kind of very similar type of pattern. But here's what's kind of interesting about this application. It's the exact same code that was running before. But instead of being like 97% in the idle task, we're now 99.75% in the idle task. Okay. So we've saved ourselves at least 2% already just by switching from a periodic tick task, using a periodic system tick for our scheduler versus a cycle-based scheduler. Okay. So we're already kind of recouping some time there that would have been wasted cycles, wasted energy. And again, for battery-powered devices, this is absolutely critical. Now, these examples, I'm not showing you where we're going into the low latency and high precision side of things, where we're going into the sub-millisecond space, but that's something that you totally could do with a cycle-based scheduler. In fact, there's no limitations on how small of a cycle you can go to schedule something. Okay, which is quite interesting. If you need something to happen, 10 CPU cycles after, some event occurred, you could schedule that kind of thing. Now, is that realistic for a real application? Probably not, but there's a lot of capabilities built into these cycle-based schedulers that I think are totally worth exploring. Okay, now that you've seen the differences between the periodic scheduler using the system tick and the cycle-based scheduler, let's talk a little bit more here. Okay, what is happening there is that you can see the system tick doesn't actually occur on the cycle-based scheduler until that one-shot timer actually expires. Once it does, then the RTOS behaves exactly like your RTOS did before. Okay, it's going to run the kernel. It's going to figure out what task needs to run. It's going to run it. It's going to look to see when the next task needs to occur or when the next system tick, and it's going to set up the code and then let it, it's going to then run from there. Okay. So once you hit that one-shot timer, the RTOS behaves the same. The difference is that when it resets that system tick, it's not going to be a periodic rate. It's actually going to calculate the difference there. Okay, on when the next one actually needs to occur. Okay. So I hope that has given you a little bit of insights into how you can use cycle-based scheduling. And again, this example used embOS-Ultra and it compared it to embOS-base. Okay, embOS-base is very similar to what you would find in other real-time operating systems and open source ones that are commonly used throughout our industry. Okay, and what we kind of saw, I think, today comparing these two, first of all, we saw that the timing resolution could be dramatically increased if you wanted to. You can improve the latency of your code. We certainly saw that you can improve energy consumption, right? We saw that the periodic scheduler was using was 97% idle, where when we switched to cycle-based, it was 99.75%, right? So all that extra overhead from the kernel and from the system tick constantly running is completely thrown away, okay? And you actually gain all of that back, which, again, if you're worried about energy consumption, that's something that can increase battery life or just decrease your energy profile and help improve your device's use of the grid, essentially. All right, so those are a couple of ideas there to get you started. What are your next steps? Well, if cycle-based scheduling is of interest to you, I would highly recommend that you try to get hands-on with it. Okay, check out the embOS-Ultra RTOS user guide and reference manual. I'm going to put the links here below so that you can actually just click on those and go check them out at SEGGER's website. You'll see what the difference in the APIs are. I know when I first started to play around with these, one of my big concerns was, well, if I really do like cycle-based scheduling, am I going to have to go back and like re-instrument all my applications and all this stuff? It's going to be a bunch of work, right? I'm kind of worried about that. Well, if you actually look at the differences, porting from a traditional RTOS into using a cycle-based one like embOS-Ultra really isn't a big deal. Okay, I actually talked with the folks at SEGGER a bit, and tried some stuff out myself, and I'll tell you what, it was pretty simple to move things over. If you're already using embOS base, the transition was completely seamless. Whereas if you're using kind of a common RTOS that might be out there, you do have to go and update the APIs that you're using. And maybe a couple of files that bring in the RTOS and stuff like that. But I'll be completely honest, it's not a heavy lift, okay? It's something that can be done fairly quickly. So I won't let that stand in my way. Even as I saw in putting these demos together, it was very straightforward for me to get that working, okay? If you don't want to set something up right now, you can also still check out an example that's set up in a simulator, okay? So what I just showed you, I actually pulled from simulator example code that was on the SEGGER website, okay? And so I've got a link for those again below that you can check that out. You can run it in the simulator. I didn't want to show you the simulator run because I wanted to use system view so you could actually see what the differences were between the periodic ticks visually and then see what it was with the cycle-based, all right? And so we were able to look at that. So I actually took the simulator code and then I made some modifications so that it would run on an mPower board. And then that was what I actually showed you there today. So, and certainly you could port that to any board that you want. Okay. From there, other next steps, honestly, if you see that the cycle-based scheduling could be important to you to save energy or to improve the latency and timing of your RTOS tasks, maybe to help you integrate your code into one nice architecture instead of having multiple architectures running where you're RTOS based and then some stuff outside of that to get your high precision, then take a look at this in a little bit more detail. And I think you'll find that not only is it interesting and innovative, it's also quite helpful in a real professional product development cycle. So with that, I hope that you found this to be pretty interesting and you have a little bit more appreciation for what cycle-based scheduling can give you. Now, you can certainly try all of this out yourself. You'll actually find in the description below, I've included links to all the different software packages and tools that I use to put together this demonstration, this video. So I'd highly recommend that you check out those links, check out the tools, and try it out yourself. There's nothing like learning a new technique than actually applying it and seeing whether it works for you in your own development cycle. So with that in mind, thank you for your time and attention today. I hope you found this to be interesting. If you want to hear a little bit more from me, you can certainly subscribe to this channel and also follow me on LinkedIn, where I daily share tips and tricks about how to develop embedded systems successfully. So with that in mind, I wish you the best of luck and I look forward to talking with you in the near future.